It's time for us to start. I hear this is very informal, and feel free to interrupt and ask questions too. I like questions, although it's kind of dark in here, so shout out questions when I slow down. Just to introduce myself, I'm at the University of Washington. I'm the state seismologist as well as running the network for the Pacific Northwest, although actually in 2 weeks I'll be switching to run the Earthquake Center out of Southern California at USC. So my colors will change. And I need to recognize Iris and SSA that facilitated this talk. They arranged the logistics and brought me over here. Iris is Incorporated Research Institute for Seismology. They're going to run the data center and the instruments for the seismologists in the U.S. And SSA is the professional society, Seismological Society of America, that started basically the time of the 1906 earthquake to make sure we were organized and had journals to read, things like that. Just a quick outline. I'll try to talk for 20, 25 minutes and have some time at the end, but as I said, just ask questions as they come up. I'll start with a little bit of the science we're trying to do in Washington, and then talk about the plate tectonic setting we have in the Pacific Northwest. Then talk about the hazard and how the earthquakes translate into where it's most dangerous. And then I'll talk about the early warning system we're building that I have on my phone now, but you might have in a year or two, assuming everything works out. It's in Washington and so forth. And then a little bit about kind of status of where things are. Okay? So and then before you even talk about the science, I just wanted to mention my background. I started out in physics as an undergraduate, and it was kind of boring, a problem set every week for every class. And geology showed up with field work and computer simulations of things that are actually in the earth and instrumental studies and actual hazard implications. And I have to say I'm very happy I got into seismology, although that plot that you see up there is one of the bigger kind of artifacts we've ever made in earth science. It's the Palmdale Bulge. It's from the 70s where they thought the ground in the desert near Los Angeles was swelling up because it was all cracked and ready to break. We're going to have a disastrous earthquake. And seismologists promised to be predicting earthquakes by the 1980s. And as you, I hope, realize, we're nowhere with earthquake prediction. You can read all kinds of things on the web about crazy earthquake predictors, but practically, the best we can do is talk about earthquakes that are likely to be in the next 50 or 100 years. Okay?
Question.
Yeah?
How would you compare the state of earthquake prediction to the state of eruption prediction?
Oh, eruptions are way ahead of us. With eruptions, generally before an eruption, the ground swells up, and often there are earthquakes in response to the swelling. And if you're lucky, you know where the magma is, and you can sort of interpret the seismicity and the motion. So I think the general sense is like 90% of the eruptions give some warning that something might happen. Like St. Helens, 6 weeks beforehand, they evacuated the area. They kind of guessed wrong in 1980. It blew out the side and went way farther than they thought, but they had a strong suspicion something was coming. But earthquakes, half the time they're foreshocks, but we can't tell foreshocks from earthquakes that aren't followed by earthquakes. Every time there's an earthquake, it might be a foreshock. So our predictability is very weak for earthquake hazard. So, yeah. Let's see. So at the University of Washington, one of the ongoing projects is IMUSH, imaging magma under St. Helens. Not what I'll talk about today, but just the sense of the kind of excitement in the science of trying to see where is the magma under St. Helens, what's the plumbing, how does that relate to the faults in the region, and trying to image that down into the mantle, down to 100 kilometers under the surface. Because so far we only have a good idea for the top 10 or 20 kilometers. So we have 5 institutions, 3 kinds of data. In a year or two, you might hear if we figure anything out. And another kind of sidelight here is the most famous work we've done since I've been there. It's actually got to 3,000 news outlets. Is when we discovered the Beast Quake. And for people who aren't football fans, that's when Marshawn Lynch kind of takes the football and runs about 80 yards down the field in some critical game to score the decisive touchdown. And that's the seismogram we recorded. I was really impressed before I figured out that was across the street. The seismometer moved about a micron or two. but it helped build the reputation of CenturyLink Field. And I interpreted this for the Seattle Times, a little bit of imagination there. Let's see, so another advantage of seismology, my parents get to see me on TV. I realize I'm doing something useful here. This is John Stewart quoting me about fracking to kind of make fun of me. So people know we're doing something relevant, if not useful. But the real reason to have the seismometers and the seismologists is the seismic hazard, and this is the map for the country. So you can see the red, which means the Pacific coast is the highest danger. The Wasatch Fault a little bit to the east, and Utah has got about a tenth the rate of motion on the faults. It's also dangerous. It runs right through all the towns in the region there. And then there's some bullseyes on the east coast, generally where we saw the last earthquake, which isn't necessarily where we'll see the next earthquake. And there is actually a fault up there near New England, near the Canadian border. But the west dominates. And we can put numbers on this. So this is kind of the point. In the Pacific Northwest, Oregon, and Washington, there's about $500 million a year in expected damage from earthquakes. And you're probably wondering, where is this damage? And, it comes every couple hundred years for the worst cases. So most years there's zero damage, and every now and then there's tens or hundreds of billions of dollars worth of damage. And it's this danger that lets us study the science and the hazard of earthquakes. You see, California actually dwarfs the Pacific Northwest with $3 to $4 billion of damage per year. And that's why we can spend a few tens of millions a year studying and trying to tell people what to protect in the event of earthquakes. Okay, any questions on this? And so, we always argue with Alaska, which doesn't even make this plot, because they have, way more earthquakes than we do. They have almost nothing to damage. So that's often the argument with the Alaskan senator versus the Oregon and Washington senators about who gets the new resources.
I have a question.
Yeah.
The dark red to the lighter red, where's Portland in relation to that?
Portland. So Portland, it's kind of, right here.
Oh, good, we're
So
not
it's
in
right-
the heaviest part.
Yeah, it's,
Oh, good.
and you'll see a more detailed map, but the coastline is where you don't want to be in a
Oh,
big
right.
earthquake for a lot of reasons. And, here, you'd much rather be in Portland than over in the Tualatin Basin, a little bit to the west, because you'll see why. And Puget Sound's where you also don't want to be, so you'll see that too. Yeah.
Cost per year because of earthquakes? Or
Yeah, it's, so along the whole west coast, it's about $4 billion a year. And, you really haven't seen it. You have to go back to the San Francisco earthquake of 1906, which, destroyed the Bay Area, or the Northridge earthquake, which cost about $50 billion. Loma Prieta cost about $20 billion. But most years, there's almost no damage. And then you'll see at the end, since I came to the Northwest, the earthquakes have stopped. So when I go back to California, we'll see what happens. Yeah.
I was curious what features account for the lower hazard in the middle of California?
The middle of California, yeah, that is, well, there's faults on either side of it. So there's the Sierra Nevada mountains on the east, and that's kind of got a big fault lifting up the mountains. And there's the San Andreas on the west. So it's really between the two major faults in the region. Okay? Let's see, so here's the plate tectonic settings. For those of you who haven't seen plate tectonics recently, in the middle of the Pacific Ocean, we have this ridge transform system. So two oceanic plates are moving apart. They're moving about an inch a year. And what that's causing is this Juan Fuca plate. So it's this plate plus the crust and the mantle underneath it. It's kind of moving this way about an inch a year underneath North America that we're standing on. Okay, so this boundary right here has an inch a year of motion, and every 500 years we get an earthquake on it. But this is the general picture, so we'll zoom into the details of this in a minute, okay? And then if you look at a cross-section through this area, you can vaguely see the Puget Sound up here on top of it. Here's that boundary between the North American plate and the Juan Fuca plate. And, this shallow part's cold, and when it's cold, it's brittle, and when it's cold and brittle, it kind of locks. And again, it locks for about 500 years. Every 500 years, it jumps and moves about 10 yards, 10 meters, all at once. once all along the way from Northern California to Canada. So that's our magnitude 9 earthquake. And if you stay through two more speakers, Chris Goldfinger's, the world's expert on this subduction zone, and he'll talk about it in detail. Oops, what have I done? Okay. And scientifically, it's interesting that deeper, if you go deep enough, it's just moving continuous. It's like molasses. You just kind of push on it and it slowly moves. Nothing much to see. It's anomalous. But if you go right underneath our feet here, there's a zone where instead of being locked for 500 years, it's locked for a year. So about once a year, it moves about an inch. And when it moves an inch, it takes about 2 weeks to do it. And so it kind of rumbles, and we can see it on the seismometers. This is this episodic tremor and slip you might have heard about. And so this is a zone that's scientifically very interesting because we can't for the life of us figure out why it takes 2 weeks to happen. We know why the shallow earthquakes happen. We're still trying to figure this out. But the motions are so weak you won't even feel them. So as far as hazard goes, we wonder if these events that happen every year might trigger one of these, but probably not, we don't know. It gives us something to do. This is where the danger is, up here in the shallow part. Okay? And this shows where that tremor is located. All those little red dots or spots people have located the tremor. And the point is, it goes right under Portland, it goes right under the Puget Sound, Vancouver Island. It's kind of continuous all along this Cascadia subduction zone, whereas this part that's further out, and mostly offshore, is where it's locked and has the great earthquakes. Okay? So when Chris talks in an hour, he'll tell you what happens exactly here. But this just says there's slow rumbling under our feet every now and then that you'll never feel. So that's kind of a sidelight. So back to the hazard. And here's a more detailed hazard map. And again, the shaking along the coast is where it'll be most violent. And of course, if you stand on the coastline after a big earthquake, you'll get half an hour see a big wave come in. Mostly not as big as the one in Japan. That was the biggest one we've ever seen, 40-meter high wave in places. But still, you don't want to be standing on the coast. You can also see that there's activity in Puget Sound. There's some down by Klamath Falls. There's a lot of faults under Portland. And there's the fault system that runs through Hanford Nuclear Reservation. So that's, yeah. And partly this is because we study these areas carefully. You notice there are more faults here and here. But partly there is an active fault that runs right through Hanford. It moves very slowly. So, it's a danger with the reactors where people have very high levels of safety. It wouldn't really be nearly the risk we have in the I-5 corridor. Okay? Again, you just jump in with questions if you have them. Okay, so our seismic network, this network I manage has all of Oregon and Washington, about 400 seismometers of a lot of different varieties. To replace the whole thing would be about $15 million. But as you'll hear at the end, we're doubling this to do our early warning system because we need better instruments and connections. We work from the UW with the people in Eugene at the University of Oregon, and we also work with partners in California and Canada to make sure we have their sensors plugged in to surround any of our earthquakes. But that's our basic seismic network. And if you go to our website, one more slide I put in. One of our goals in the next 10 years or so is to do what Japan is doing now, which is to put a cable offshore. Because as you saw, the big earthquakes happen under the sea, and we'd like to get instruments right on top of them to monitor ongoing activity and see where things are stirring. But that's very expensive. The estimates for this are about $500 million, and the extra knowledge we will get is something we're still trying to demonstrate. So, and there may be cheaper ways to do this. But Japan is putting one in right now, partly because this kind of thing is right off of Tokyo. Tokyo's sitting right on top of a subduction zone, so they invest more than we do in their instrumentation. Yeah?
How are your sensors powered?
Well, here there's a cable that just runs right through all the instruments. We just power from the shore. And you can also, with the wire, collect the data, so you have the data at the speed of light. If you don't pay hundreds of millions of dollars for cable, you have to put the instrument down there with batteries and go down and get the data once a year, which is a lot less useful to tell what's happening this month. And then there's more complicated ways where you can put instruments on the seafloor with batteries, acoustically couple them through sound in the water up to buoys, which then talk to the cell phone network, which is cheaper but complicated, and that's what people are experimenting with now. Yeah.
Couldn't you use NOAA?
Yeah, we need to have instruments on the seafloor to tell the emotions, and then there's a need some way to couple it to the surface. And NOAA does run these dark buoys, but they're generally farther offshore. They're so far offshore that they have them out there to look at the tsunamis, but they're so far offshore that they're only good for the tsunami that's going out. The one that's going in is already hit. They like to put some sensors, just like we'd like to put them here. We'd be working together with this cable, and then we could warn the people on shore what was happening. It's a little bit of a battle because, right now they tell people you feel the shaking run uphill, which, is good advice. Of course, we'll know better what's happening if we have instruments right on top of it. So it's an ongoing discussion. Let me ask, is Chris here? Chris Goldfinger? Because I have to watch what I say once he comes in. Yeah, because he has geology he'd like to do to tell us about the seafloor, and we'd like to measure it to do the geophysics, and they both help. Yeah.
In the event of an earthquake, would the hypothetical cables you're looking to lay down be vulnerable to damage and disruption from said earthquake?
Good question. That's an excellent question. And, and that's the problem. And we can see in earthquakes around the world. Taiwan has some cables, and last time they had a big earthquake, a bunch of their cables broke, and so we put out loops to try to have more than one path back to shore, but as the rupture comes through, some instruments would break, and that's actually an advantage of these buoy systems, because they shake, but they don't get their cord ripped off. So yeah, it's a consideration, and not an easy one, because these canyons, as Crystal talked about, have these landslides that kind of rush down. Okay, so I can't get anything past this crowd. Oops, wrong thing. So if you go to our website, you can see the seismograms from our stations. You can see what from the impact of an earthquake just happened, what the distribution of what people felt is. You can see catalogs of earthquakes for your area. So that's all on the web. Then coming back to this, the earthquake dangers are kind of threefold. In our region, we have that big fault along the coast with most of the motion, but we also have these faults in the crust, because there's this big plate boundary that's deforming, it also crunches up the crust a bit. And we also have earthquakes with the magenta dots here. These are the ones that are within the subducting Juan Fuca slab. As it goes down, it kind of buckles a bit, and that's what we had in the Squally in 2001, as well as two previous ones that were similar. Okay, so there's three kinds of earthquakes, and here's the faults around the Puget Sound. You can sort of get an idea how common they are by the fact one's called the Olympia Fault, one's called the Tacoma Fault, one's called the Seattle Fault. South Whidbey Island Fault runs up through a bunch of towns. There's a fault through Bellingham, one in Vancouver and Victoria. So the crust is just shot full of faults. And tectonically what's going on is, aside from the major boundary, Oregon's kind of squeezing Washington against Canada. So it's squeezing a little bit, and all these faults are accommodating that. Okay, just a little bit of motion. So these are slow faults, but they're dangerous faults. And the Seattle fault is, of course, the one we fear the most. It runs right along the south edge of Seattle, right under the stadium, so we think. Actually kind of a zone, but then yes, the stadiums are built like a fortress, so they're at least of our worries. But this fault had an earthquake about 1,000 years ago. This is more than magnitude 7. Seems to extend from Sammamish, Bellevue, through Seattle, over to the sub-basin, Bremerton, places we don't really want damaged. And a student of mine at one point modeled what would happen if this earthquake happened in the wet season, just actually a 6.5, not a 7. And you can see the landslide distribution that would happen on all the bluffs around Seattle. So not only with the shaking kind of wrapped down, the landslides would cause damage as well. Okay? But these faults move slowly. We don't know if this fault moves every 1,000 years or every 5,000 years. In 7s, and then how often do we have magnitude 6s, and it still cause a lot of damage. This actually dominates the risk for the city of Seattle for anything less than a very big structure. The big structures are more vulnerable to the big earthquakes on the coast because they shake it at the period that those big structures resonate. Okay? Yeah?
What kind of faults are these? Are they normal, crust, or
Yeah, okay, these are thrusts, so when the Oregon squeezes Washington into Canada, it makes a set of thrust faults. And this one under South Seattle is basically thrusting the mountains to the south up over the Seattle Basin. Okay, any other questions? And so then the second kind of earthquake I showed, those magenta dots, or 30, however you count it. This shows every earthquake deeper than 40 kilometers depth in our catalog. And you can see that they're distributed all the way from Canada down to California. You could have them under Portland or Salem or Eugene, but most of the dots are under the Puget Sound. It turns out as that plate is going under the coast, it's bending a little bit. And so we're in like a tablecloth at the corner where the subducting plate is bending. That's where we get these deep earthquakes. They're about 30 miles down. And you see these three red dots. That's where we have the 1949, 65, and 2001 earthquakes. So each of those caused a lot of damage around southern Puget Sound, Seattle, Tacoma area, and Olympia. Luckily, it shakes the state capitol every now and then. So again, there's Chris. He'll be here in 2 talks, and he'll talk about that major fault, kind of the biggest concern because it disrupts the whole Northwest, although these crustal faults will more intensely damage the cities in a small area. Okay? So hang around to hear Chris. And he's kind of a rock star. He's in all sorts of movies and TV shows and things. He sails boats around and digs up the seafloor. And I need to mention that one of the reasons that the earthquakes are dangerous is because we have these deep sedimentary basins. And these figures are kind of hard to orient, but here in the Seattle Basin, this is kind of the fault that's at the south edge of Seattle. And then if you go about 30 or 40 miles to the north, you come to the north edge of the basin. And it's about a 100-kilometer east-west basin, and it goes to a depth of about 10 kilometers. So basically, something's pulling down the ground there. It fills with dirt from erosion, and that dirt's softer than the rock, and then when the area shakes, it shakes like a bowl of jello, okay? It shakes more than the surrounding area, and so we have to be particularly concerned with structures in the basin, which means in the big cities of Puget Sound. And here in Portland, there's not so much of a basin. It's pretty thin. We argue about how active the faults are on the basins. But it's clear there's a big basin off to the west. This is the Tuolumne Basin, and it's on the scale of the Seattle Basin. And it's right where the Intel plant is built, for example. So there's a lot of motivation for us to study that as well. And this is an actual example of the motion outside the basin on the left and inside the basin on the right. It's a seismogram. It lasts about a minute. You can see outside the basin there's pretty weak motion for a couple of seconds. Inside the basin there's 3 or 4 times as strong motion lasting about 50 seconds. Okay, so it really does amplify and prolong the shaking of structures that worry about the kind of resonant frequency of the basin. And so when we're talking to the public, a lot of us don't like to use numbers, but when we're talking to the engineers, we have to use numbers because that's what the building codes are built on. So here are the numbers. So for the big earthquake on the coast, the magnitude 9 that breaks the whole zone, there's about a 10 to 15% chance every 50 years. I think Chris will tell you 15 to 18 in an hour. So you might see it, you might not, in your generation, your children's generation. On the other hand, the southern end of Cascadia, so from middle Oregon to the south, seems to have earthquakes about twice as often. So they have about twice the odds, 25 to 40% chance in the next 50 years. You or your kids may well see one down there. Luckily, there aren't many towns on the coast down there. So those are the odds for that. The earthquakes like the Nisqually earthquake have the odds much higher, since you can see we've had 3 of them in the last 100 years. It's about an 84% chance of having one in the next 50 years, and we'll probably have more than one. That's why we're rushing to fix the 520 bridge and the viaduct, because those are projected to be at serious risk if we have one more earthquake like Nisqually. And then the crustal earthquakes are infrequent because the fault motion is slow. So across the entire Pacific Northwest, it's about a 15% chance of having 6.5 on one of the crustal faults. Okay, so All make sense? So that's what we tell the engineers, and they make us give them a number. And when an earthquake happens, this is kind of the sequence of events. The computers are looking at the data all the time. When they've looked at it for a minute or two, they notice when there's been an earthquake. They're not very quick at recognizing this, but in a minute or two, they produce a magnitude and a location that we wouldn't want to tell the public because it's often wrong. So it does go to the emergency managers and goes to our cell phones, and we jump on our computers and smartphones and check and get some numbers we have confidence in, and then within 5 to 10 minutes, we put it out on the web and call the emergency managers and correct mistakes we've made. And the reporters start calling as soon as they feel shaking. And so the last time we had an earthquake, it was notable. They woke up the guy who was supposed to be listening. Anyway, the reporter is the one that told us there was an earthquake, so we looked, and sure enough, there was an earthquake. But what we're doing now is this earthquake early warning, and the goal of this is to notice the earthquake within 5 or 10 seconds of when it happens, which means it's got to be entirely automatic. And it has to be accurate enough that we can send it to things that will stop traffic and turn off computer systems and things. So that's our current challenge, speeding up this whole notification and by an order of magnitude or two. And early warning works, like this. A fault breaks, and we want to warn the city. So one advantage is we can put the instruments closer to the fault. These waves go a couple of miles a second, so you can pick up a couple of seconds for every couple of miles away the city is. And we can also see the initial waves. The P waves that come first are about a quarter as big as the shear waves that come next, and surface waves that cause the damage. So if we see the P waves, we can tell what's happened, guess the magnitude and location, and guess the S waves that are coming right after them. So between having instruments close and judging from the P waves, we can get some time to try to warn people. But we only have a few seconds to get the estimates of what happened and to tell people what's going on.
Question.
Yeah.
Are you trying to use machine learning to recognize earthquakes?
Well, the thing, machine learning is kind of less appropriate for this because we know what we're dealing with. So, we know exactly what the earthquake should look like, except for some noise. So we're not blindly trying to interpret the data. So, we have things we try to do with machine learning. If we don't know what's happening, we can use that to try to estimate.
No, I was just thinking for an automated system.
Yeah, it's going to be automatic. It's going to take the signal and interpret it without people, but it's going to interpret it kind of, it's like your speedometer. It's a big signal with big magnitude. It's not going to be too much of, we're not going to be learning with the machines, we're just going to be reacting with the machines for this case. Okay, so let's see. So then if we have the early warning, there's a lot of things we can do. You can't do much with a few seconds or even a minute of warning. You can't get out of bad buildings reliably. It's hard to even distribute information to some things. But you can slow down the traffic. Yeah, 5 minutes, okay. You can slow down traffic. You can get emergency crews into operation. You can get companies to kind of put their fragile equipment into a more safe position. The computer companies say it just takes like 5 seconds to switch Google's operations from here to China, and they may never come back. But there's a lot of reasons to have a warning of a few seconds. And of course, most of it's telling people too that it's about to shake. Look around, find your kids, turn off the stove. Because half of what happens in earthquakes is people break their leg or step on glass, or something happens where if they just had their head up and knew what was happening, it wouldn't happen. And a lot of countries are doing early warning. Japan's got a sophisticated system they've had for a decade now. China's building one that's fracturing $1 billion. We tell the congressman Mongolia has one. Maybe we should build one in the U.S. But it's true. They have one. So the logic is pretty. The people are buying it. The BART trains are a clear example. They're expensive trains. They're full of people going 70 miles an hour at rush hour, and the trains are one of the few ways you can get around the city if the surface has been really fractured by an earthquake. So they're investing billions in trying to make BART safe. So we have a plan that's $16 million a year. We have $10 million a year now, but then Trump kind of zeroed it out, but the Congress is going to put it back in. So we think sometime next year we'll start operation of this early warning system. That's our best guess, and we'll keep improving it for the next few years until it's up to the what's feasible and worth the investment to do. Okay, I've got it on my phone now. It doesn't perform all that well, but in fact, it's hard to send a signal to more than a few thousand people on an app at the moment. You know, we'd like to send it to 50 million people, but we actually don't know how to do that. It's built into Japanese phones, but we're negotiating with the phone systems to try to get like 2 bits of information, an earthquake or a strong earthquake or nothing, or we're taking it back. So we're trying to figure out how to get the signals out to a lot of people quickly, and it's a challenge. Okay, so the last note here is that, you know, when I came to Washington in 2006, and I brought a network manager who came from Memphis, I came from UCLA. They promised us a magnitude 5 earthquake every year, and you can see the history here between the earthquake in Salem, a couple in Klamath in southern Oregon, Duval and east of Seattle, Satsat and Squally. We had, and a lot of 5s as well. And since then, we haven't had an earthquake over 4.6. So that's kind of the history, and that makes it a challenge. So that last point, just the points I hope I made, you know, we'd like to keep people's attention that the earthquakes are likely to come eventually and need to be ready, but we haven't had any in a decade. But I hope I also made the point that, you know, for scientists, you know, we have a blast here in the Northwest, the volcanoes and the subduction-zone and all the mountains and things. I think I pointed out the several kinds of earthquakes, crustal and the deep ones within the plate and the coastal earthquake. How much, you know, we know and don't know about what to expect next. And one of the main things that we need to do for earthquakes is fix these unreinforced masonry buildings in the cities. That's kind of the biggest vulnerability we have. We know that a lot of buildings that were built before we knew how to build them are just going to crack and fall apart if there's a serious earthquake near enough to them. And finally, I mentioned the early warning system that we're working on now to at least give people a few seconds or even a minute of warning to prepare for the shaking. Okay, that's all. Thank you.